Optimization Unit, Lesson 2.7. Target Objective, Optimizing Function, and Answering the Question. The target objective is the search for the optimal solution. It's either the search for the highest value, a maximum, or a lowest value, minimum. The optimal value is obtained by using the optimizing function. Remember when we started this unit, we laid out a 10-step process for optimization. We're now at step 7 of that process. Up until now, our problems have included descriptions of constraints on the x and y variables that we translated from English into mathematical inequalities. The hardest part is typically decoding the English so that we can represent it mathematically. The math isn't hard, it's the English language that's hard. I blame Shakespeare. We're now going to have an additional piece of information added to the problem which tells us what the target objective for the problem is and a statement, usually related to money, that will translate into the optimizing function. In each optimization question, you'll be given a statement about money, cost, profit, etc. This becomes the optimizing function. To find the maximum or minimum points in our optimization problem, we take the x and y coordinates from each vertex in the polygon of constraints and take turns putting them into the optimizing function and solving, which gives us a value for the optimizing function at that vertex. After you find the value of the optimizing function using the coordinates for each vertex, the largest value indicates the vertex where the optimizing function is at its maximum, and the smallest value indicates the vertex where the optimizing function is at its minimum. If we return to our steps, we look at step 7 is to identify the target objective and write the optimizing function. If you go back to the question and pick out the sentence that has to do with money, that's what you're going to turn into an equation, and that becomes your optimizing function. Be careful, you don't want to use a statement about money until this step, so ignore it when you're creating your graph and finding your vertices. That statement doesn't become one of your constraints. In other words, it's not part of your polygon of constraints. Step 8 is to use the optimizing function at each vertex. So you take each vertex one at a time and replace the x and y in the optimizing function with the x and y coordinates of the vertex. Step 9 is to choose the maximum or minimum depending on the vertex. So of all the values you get out of step 8, you choose whichever one is largest or whichever one is smallest. One of these vertices gives you the maximum, and one of them gives you the minimum. Finally, step 10 is to write a concluding statement answering the question that was posed in the initial problem. The question may ask the maximum, minimum, or number of items that give you a maximum or minimum. For example, the question might ask, what is the maximum profit that's possible in this situation? Or, how many jet skis must they sell to make the greatest profit? The first question requires an answer in dollars, and the second question requires an answer in number of jet skis sold. Or you might be required to answer both questions. So let's look at an example. Determine the vertices of the polygon of constraints given the following scenario. A bag contains red and blue marbles. The bag contains a maximum of 12 marbles. The bag contains a minimum of 6 marbles. There are no more than twice as many red marbles as blue marbles, and the bag contains at least 3 red marbles. If each red marble is worth $1.50 and each blue marble is worth $3, what is the maximum value of the collection of marbles in the bag? How many of each marble do you need to have the maximum value? So let's go back and approach this problem right from the start. The first thing we need to do are define the two variables. So we've got red and blue marbles, so we're going to go ahead and start off with let x be the number of red marbles and let y be the number of blue marbles. The next statement, the bag contains a maximum of 12 marbles. So that means the total, all the marbles, x plus y, has to be less than or equal to 12. The next constraint says the bag contains a minimum of 6 marbles. So that means the total again has to be at least greater than or equal to 6. So it's got to be, you could have 6 or you could have more than 6. The third constraint says there are no more than twice as many red marbles as blue marbles. So the first question we ask is, which one do we have the most of? Do we have more red or more blue? In this case, it says we have twice as many red marbles as blue. So our approach to coming up with the constraints is to put our x and y and then figure out which one is largest and put the modifier onto the other one. Here we said that the red was the larger, so we're going to put the multiplier 2 onto the y value. Now we need to go back and look and see which way does the inequality sign go. So there are no more than twice as many red marbles as blue. So when we say no more, that means less than. It can't exceed that. It can't go larger than that value. So this tells us now that the number of red marbles is less than or equal to 2 times the number of blue marbles. The final constraint says the bag contains at least 3 red marbles. So we take our variable for red, which is x, and it says there has to be at least 3 red, so it's going to be equal to, but it could be larger than 3 as well. So x, the number of red marbles, can be greater than or equal to 3. Now, the final 2 constraints we need to always check in on: is it possible to have negatives? Can we have a negative number of red marbles or a negative number of blue marbles? Of course, the answer is no, we cannot. So that means our x value always has to be greater than or equal to 0, and our y value also has to be greater than or equal to 0. So with that, we've laid out all of the equations of our constraints. Now we can go ahead and start graphing them. So we take our first equation here of x plus y less than or equal to 12. We need that to get that into the y equals ax plus b format in order to graph it. So we're going to subtract negative x from, or we're going to put negative x from both sides. So we end up with y less than or equal to negative x plus 12. We have to do the same with this other equation, so we'll do them all at the same time here. We end up with y greater than or equal to negative x plus 6. And finally, our 2y, x less than or equal to 2y, we're going to change that around to be 2y greater than or equal to x. So y is greater than or equal to 1/2 x. Now we can go ahead and start graphing. First equation here, our y-intercept is 12. Our slope is -1, so we go down 1 and over 1. That gives us our 2 points. We can now go ahead and connect those 2 dots and form a line. Once we've graphed our line, we need to look at the inequality sign. So we've got y less than or equal to. So we've got a solid line because it's potentially equal to. But with the less than sign indicates that the shading area is down below the line. So that's the area that's possible given that constraint. Now let's go ahead and look at the next equation. Y greater than or equal to negative x plus 6. So again, we've got an equal sign, so we know we're going to have a solid line. We're going to start at a y-intercept of 6. And the same slope as the last line is -1, so we're going down 1 and over 1. And then go ahead and connect those 2 lines. Again, looking at the shading, this time it's greater than, so the shading is going up from that line. Looking at our third constraint, y greater than or equal to 1/2 x. In this case, the b value we've got is 0. So in the y equals ax plus b form, there is no b value here. So when there's no b value, we can assume it is 0, which gives us a point at our origin here at 0. And our slope in this case is 1/2, which we can always see as rise over run. So we've got a rise of 1 and a run of 2. So a rise of 1 and a run of 2. Put another dot and go ahead and connect those with a line. Now we have to ask, where does the shading go with this one? Again, we've got y greater than or equal to, so we also have a solid line, and the shading goes above the line. Okay, so for the x greater than or equal to 3 constraint, again, we've got an equal sign, so we know we're going to have a solid line. There's no y value in this equation. So when there's no y value, it means for any y value, x is always going to be greater than or equal to 3. So we put x equal to 3 on the axis. And in this case, we have a vertical line that goes up from there. Now we look at the shading on this one. It's x greater than 3, so that means, you look to the right-hand side where 4, 5, 6, all those numbers are greater than 3. So that means the shading we've got is going to be on this side. So the final two constraints that we added in that are usually always there are x greater than or equal to 0 and y greater than or equal to 0. So that's the x and the y axis. So x equal to 0 is the y-axis, and y equal to 0 is the x-axis. And in this case, everything has to be larger than those. So we indicate the arrows up from the x-axis and to the right of the y-axis. So from all of that now, we can look and see which area all of the arrows are pointing to. And if we look very closely, we can see the yellow arrows here, the blue arrows coming down from the red line, the green line, and the blue line. And so we can see that the area inside here is what is being indicated by this system of inequalities. Once we've identified the polygon of constraints, now we're going to identify the vertices. We're going to name all of the vertices for this polygon. So we're just going to give them letters A, B, C, and D. And in the next step, now we're going to find the coordinates of each of those vertices. So let's start with vertex A here. We can see that it's the intersection of the blue line and the yellow line. So the blue line was y greater than or equal to negative x plus 6 and x greater than or equal to 3. So let's go to a new page and we'll find the solution to that set of equations. So when we've got two equations with two unknowns, the solution to that set will give us the point of intersection between the two lines, or the vertex in this case, to the polygon of constraints. The first equation we're going to be working with is y greater than or equal to negative x plus 6. The second equation we said was going to be x greater than or equal to 3. In this circumstance, we can see from the three methods we learned for solving linear systems was to take the x, because we've got x alone, we can substitute that in to the original equation. So we're going to use the substitution method to take this x value and substitute it into this equation. So we end up with y greater than or equal to negative 3 plus 6. So that means y must be greater than or equal to 3. So the coordinates of that vertex then are vertex A are 3, 3. Looking back to our system, this kind of makes sense from what we see on the graph. We've got 3 and 3. Now let's look at vertex B. Vertex B is the intersection of that same yellow line, x greater than or equal to 3, and the red line, y less than or equal to negative x plus 12. Again, we can see that this lends itself to substitution. We've got x greater than or equal to 3, so again, we're going to take that 3 and substitute it into this equation. So we've got y less than or equal to negative 3 plus 12, so y less than or equal to 9. So vertex B is 3, 9. Going back to our graph again, let's look at vertex C. Vertex C is the intersection between the green line and the red line. So the red line, y less than or equal to negative x plus 12, and y greater than or equal to 1/2 x. Now in this case, we've got two equations and two unknowns in both equations. So the rule says that if that circumstance happens, we want to use the comparison method. So in this case, we take the 1/2 x and set it equal to negative x plus 12. And now we just have one variable in one equation, so we can go ahead and solve that. In this case, I think the first step I'm going to do is multiply both sides by 2 to get rid of that half. So if I'm multiplying by 2, I'm going to get rid of the half here, so I'll have x. But whatever I do to this side, I have to do to the other side, so I'll have negative 2x plus 24. Now I want to get the negative 2x over here with the x, so I'm going to add 2x to this side, which gets rid of the negative 2x there, and it makes this 3x equals to 24, so x equals 8. Once I've got a value of x equal to 8, I can then substitute that back into one of the other equations to find the final answer for y. So in this case, I'm going to use this one because I think it's a little bit easier. So y is going to be equal to 1/2 x, which is equal to 1/2 of 8, which is 4. So vertex C is 8, 4. Finally, we go back for our last vertex, vertex D. It's the intersection between the green and the blue lines. So y greater than or equal to 1/2 x and y greater than or equal to negative x plus 6. Again, in this circumstance, we've got two equations with two unknowns in both equations, so we'll use the comparison method to solve. So we've got 1/2 x equal to negative x plus 6. We've taken this side here and that side there, put them equal to each other. Following the same method, I'm going to multiply by 2 to get rid of the 1/2 x, so we multiply both sides by 2. X equal to negative 2x plus 12. Now collect the x's together, so I end up with 3x equal to 12, so it's x equal to 4. So just to recap that, to get that 3x, to get rid of this, I had to add 2x to this side, which means I added 2x to this side, which gave me 3x, and then dividing both sides by 3 gave me x equal to 4. Now I've got x equal to 4, I can go ahead and substitute that back into one of the equations to find y. Y equal to 1/2 of x, which is equal to 1/2 of 4, which is equal to 2. So vertex D is 4, 2. So the vertices of the polygon of constraints are A, 3, 3, B, 3, 9, C, 8, 4, and D, 4, 2. So we've identified all of the vertices of that polygon. Now let's go back to our original question and see what is the target objective. Well, looking at the target objective, it says we're looking for a maximum value. So that's our target objective, is to find a maximum value. So we've identified our objective. Now we need to come up with the optimizing function. We're told that each red marble is worth $1.50 and each blue marble is worth $3. So that's going to allow us to form a new equation that is the optimizing function. So I've just put these up here as a reminder of which ones are which. Now we start off with total value, and we're going to set that equal to something, some equation. So what is that equation going to be? It's going to be based on the number of red marbles and each of the value of those red marbles, and the number of blue marbles and their value. So how does that work out? We've been told that the red marbles are each worth $1.50, so 1.50 times the number of red marbles. I'm going to add that to the $3 for each blue marble, and so we end up with an equation of total value is equal to 1.50x plus 3.00y. We could probably simplify that to be 1.5x plus 3y. So that is our optimizing function. Once we've got our optimizing function, we're now going to take the coordinates from each vertex and put it into that function and calculate the value, the total value, based on that vertex. So let's start with vertex A, which was 3, 3, and substitute those values into the optimizing function. So total value equal to 1.5x plus 3y. We're going to substitute in 3 and 3, so we've got 1.5 times 3 plus 3 times 3, which gives us 4.5 plus 9, which equals 13.5. Doing the same now for vertex B. Total value again, 1.5x plus 3y. Vertex B, we said, was 3, 9. Substituting those values into our total value equation, we've got 1.5 times 3 and 3 times 9, which again, 4.5 plus 27, which gives us 31.5. Same process for vertex C and D. We found the value of the optimizing function, total value, at each of the vertices. Now we can look at all of the totals that we got and figure out which one's largest. We're looking for the maximum value, or the largest value, and it's fairly easy to see that the total value of 31.5 is the largest of the values. So that's the maximum value of the optimizing function. So the final step, step 10, is to write a concluding statement to the question that was posed in the problem. In this case, we were asked for a maximum value, so our concluding statement is the maximum value of the collection is 3150. Try the next question on your own, then come back to watch the video segment to check your answer and watch the solution.